Hey ChemExcel, this is a little review of Learning Target 1, solids, liquids, and gases, and some of those connections that you can find between those three states of matter. Okay. So this is just the particle diagrams that you have in your packet. All right, just kind of talk through like the main things you want to remember and notice about those particle diagrams. All right, first thing we see up here is shape, right? We know solids obviously can retain their shape, liquids take the shape of their container, and so do gases. All right. What's different there about taking the shape, of course, is the volume. Right? Solids and liquids are very tightly packed together, so those are going to have that fixed volume. Right? This liquid is going to take up this much space no matter what container you dump it into. If it's taking up 10 milliliters, put in another container, it's still 10 milliliters. So it can take the shape of the container, but it does not spread out to fill the entire container like a gas does. Right? So even though the particles are free to move around within the sample, right, they're still very, very tightly packed in the liquid, and that's why they cannot take on the volume of the container. Right, kinetic energy here is mostly about the types of motions. Right, when we did the solid particle diagrams, we drew some little shaky lines on them to show that they have that vibrational kinetic energy. Right, when we think about gases, all right, we know we can throw those whooshies on all those particles. All right, they move around a lot. When we think about that type of movement, we're mostly thinking about the translational kinetic energy. Of course, they can be spinning, so you're also going to get some rotational as well. All right, but it's mostly all about that translational kinetic energy there. Liquids is a little bit of everything, really, if you think about it, because they're not going very far at one time. They can get bounced around back and forth quite a bit, so you could end up with a liquid molecule that is kind of stuck more vibrating for a moment. All right, they can spin around. They've got that rotational kinetic energy, and eventually they can move. I mean, they might take some sort of crazy path to get there, right? But it can eventually work its way across the container, which means it has to have translational movement. Translational movement is the one that you would need in order to take the shape of your container. Since these don't have that translational movement, they can't move around to take the shape of the container. Okay, so that's kinetic energy there. Right, these are some of those continuums you saw back from page 3, right? If we look here, we've got strong forces we said would be holding together your solids, weak forces for your gases, right? We said if that was strongly held together, they should be tightly packed, right? And we've also seen is that liquids are more similar to solids, right? With respect to most of these things, right? Yes, they can kind of move around, but aside from that, they're basically like a solid. They are held together very strongly or they wouldn't be so closely packed. All right, that kind of moves down to this third one here, right? Closely packed. So that's our solids and our liquids. Only the gases have the particles that are actually far apart. All right, that distance is what creates the compressibility. Only gases are highly compressible. Solids and liquids, you'll get a little bit of expansion and contraction due to temperature, maybe a little bit due to pressure, but not really enough that you would actually notice it on a macroscopic level. All right, you don't typically, press down really hard on a solid and go, oh man, it shrunk. Maybe if it was a more amorphous solid, you might squish it into a new shape, but didn't actually compress and end up taking up less space. Same thing with liquid, right? We talked about in class, if you try to compress a liquid, either it's not going to move or you're going to make a mess. It's just going to spill everywhere. That's not compressing it. That's just displacing it, okay? Potential energy is right there linked with distance between particles. So if particles are closely packed, they have that low potential energy. If they're far apart, they have the high potential energy. This right here explains the difference between heat of fusion and heat of vaporization as well. Heat of fusion, all right, is about taking your solid and turning it into a liquid. Well, that's not a very big potential energy change. So your heat of fusion is going to be low. But when we talk heat of vaporization, you got to take that liquid, you got to overcome all these attractive forces, all the strong forces holding it together. You have to overcome them to turn it into a gas. So turning the liquid into a gas It's a big increase in that potential energy because of those attractive forces, right? So your heat of vaporization is going to be way higher as a result. It's much harder to accomplish, right? Hopefully you found that to be a good review of the main points from Learning Target 1. And as always, let me know if you guys have any questions, okay? Bye.